session of multi-GPU AI Train the Trainer workshop. And as you know, we are fully online. We already started on Friday, last Friday, 30th of January, and our last session will be on the 5th of February. We will be always starting approximately at 9:30 a.m. until 5:30 p.m. with a lunch break between 1 and 2. Of course, it depends also on the trainers, the Q&A sessions. We can also finish it a little bit later or earlier. So as you know, probably I'm Vlasta from CASTIEL 2 project, and together with EuroCC2, Sineca and Barcelona Supercomputing Center, we again welcome you to this workshop. For today, day number 2 of the session, for the morning session, we have NCC Netherlands, Casper van Leeuwen, and he'll be talking about very interesting topic about PyTorch Distributed Data Parallel. And in the afternoon, after lunch break, we will have NCC Hungary, Model Parallelism with PyTorch. And we will be hearing NCC Gyula Ujlaki. So thank you again for being here, and I hope you will stay with us until the end. And of course, if you have any problems or questions with Discord or with the sessions, please feel free to reach out to us. And you can reach out to us via email or via Discord. I believe all of you are already inside the Discord. I'm sharing in the chat again link to the server, so feel free to use it. Last session, I explained how to use it. We have all the channels on the left side, but if you have any problems, as I said, you can reach out to us. Okay, so that's all from my side. Caspar, floor is yours. Thank you.
All right. Thank you very much, Vlasta, for the introduction. Let me get the slides on the screen. There we go. And maybe just to set some expectation, I think we'll actually finish a little bit before 1. So yeah, you might have a longer lunch break today, but I don't think that will lead to any issues with anybody. So my name is Casper van Leeuwen. I work for SURF, which is the Dutch National Supercomputing Center. And within CASTIEL 2, we're the Netherlands, like the expertise center from the Netherlands. I'm a high-performance machine learning consultant, which means that I work sort of at the interface between HPC and AI. So I'm not a die-hard AI scientist. I'm not a die-hard HPC person. I know a little bit about both. And what I really try to do is help people getting their AI code to perform well on HPC systems. And that's, of course, also one of the things that we'll be talking about today. So today we'll talk about PyTorch Distributed Data Parallel, which is basically one of the ways in which you can parallelize your neural network training using PyTorch Distributed, which is one of the PyTorch modules. And during this session, we'll go into what data parallel actually means and how this works. You've seen the GitHub before, I assume, but just to show you again, this is the link. Maybe, well, if you're already on the Discord, I also pasted the deep link to the materials of today's there. Vlasta, maybe you can also do the same for the chat, just the meeting chat, in case people don't have access to the Discord. So I have a slide deck and I have some exercises. I think we'll do something like maybe an hour of slides first, then see if we have a little bit of a break. Feel free to ask questions also in between. I don't mind at all. So if you have a question, I guess you can raise your hand in the, how does this work in Zoom? Or just ask the question on the chat. I'll try to keep an eye on that. If I don't see it, feel free to unmute and speak up as well. That's also fine. All right, we have plenty of time, so don't hesitate to ask many questions. I love them. So the goal of today is to understand what data parallel training is, and specifically how to use the PyTorch Distributed Data Parallel module in order to do data parallel training. And I'll also try to explain a little bit what PyTorch DDP does under the hood so that you understand also how this works and not just how to program for it. But first, maybe some motivation, like why do we even need parallelization? Well, I guess you know that LLMs are all the hype nowadays, right? So they're very, very popular. If you want to train a modern day LLM, like a real top-notch LLM, it takes a ton of compute. And these are just estimates. I actually made them with an LLM because there's no published numbers on how many floating point operations were needed to train these LLMs. But you can make a rough estimate. And so don't trust the exact numbers, but the order of magnitude is probably correct. And if you would have to train this on a single modern day GPU, even if you have an H100, it will take you 2000 years. And this is even disregarding the fact that it will never fit the memory of a single H100 GPU. But even if that would not be a problem, it would take you forever. So that's clearly not an option, right? And this also, I mean, imagine what this means, right? This means that they had to use thousands and thousands of GPUs to get this done within still a couple of months, right? That's typically the training time of these big machine learning models. But for that, we need to be able to parallelize. We need to be able to use all of those GPUs and have them work on the same neural network training task. So that's also the first reason for parallelization, right? We want faster trainings because otherwise, if we want to train a serious model on a serious amount of data, and we want to get this done in a reasonable amount of time, we need parallelization. So basically, faster training enables us to train on larger data sets, which typically also leads to a better model. But it also gives us the opportunity of doing better hyperparameter tuning, right? Hyperparameter tuning is also expensive. It means you don't train the network once, but you typically train it multiple times. And in order to be able to do that, you need the computational power. And finally, it allows us to use larger and more complex models. So also models that don't fit a single GPU memory, you want to be able to train those as well. And again, therefore, you need parallelization. But before we go parallel, make sure that you optimize your serial code. And this is really an important message that I want to give you, because if your serial code is not efficient, right? If it's sort of leaving half of the GPU cycles idle because you're just bottlenecked by, I don't know, IO or something, that means you're already wasting half a GPU, right? If you then go parallel and you go to thousands of GPUs, you're wasting hundreds of GPUs. That's a lot of money. It's a lot of energy. Don't do it. So the first step before you go parallel, make sure that your serial code actually runs well on the GPU model that you want to use also for your parallel training run. So what that means is check the hardware features that your GPU supports, things like reduced precision, tensor cores, etc., and make sure that you use those. So typically every framework like PyTorch or TensorFlow has ways to enable or disable things like reduced precision. Some of it is used automatically, but some of it is really something that you have to turn on or off. So make sure to read up on that and see that you make the most out of the GPU model that you have. Another small tip is compile your models with torch.compile. If you're using PyTorch, this allows PyTorch to basically fuse different layers together if it thinks that is better for optimization. And that again helps the execution speed. Another thing, make sure that you avoid unnecessary CPU to GPU transfers and the other way around. So one way to really kill your performance is to sort of in the middle of your model, try to do a print, right? Because then PyTorch will have to get that data element from the GPU memory. It will stop all execution on the GPU, move the data to CPU, print it, and only then can the GPU continue. That's a real good way to kill your performance. And the only way to really know how well you're doing is to profile your code. So that's sort of the last piece of advice that I want to give you. Use a proper profiling tool to identify what bottlenecks you might have, right? Figure out, is my IO pipeline fast enough to keep up with my compute? Am I not doing any of these silly CPU to GPU transfers, right? So ideally, you want to see that your GPU is really kept busy all of the time. And actually, PyTorch has pretty good documentation on this, which I highly recommend you to read. It's called the tuning guide. It's not very complex. Like there's a couple of suggestions there, like for the data loader, make sure that you prefetch enough samples, right? So that if your I/O, if there's a hiccup in your I/O, you already have enough samples in memory so that your training can just continue and your GPU doesn't stall. These kind of things are all like they're small tips, but there's a lot of them covered in this tuning guide. So that's just before going parallel, make sure that your serial code runs well. Another final thing that's actually not on the slide, if you're running on NVIDIA GPUs, and if your HPC center supports this, there's a tool called DCGMI that's part of that's made available by NVIDIA. That actually allows you to query in much more detail how much work your GPU is doing. And you can even query things like, is it using NVLink? So that's the proprietary interconnect that NVIDIA has between GPUs. You can see how much memory or how much bandwidth is being used through the NVLink, how much is going over PCI, how much is going, how much the tensor cores are being used, etc. So it's a really good way to show in real time like what part of the GPU am I actually using. So yeah, if that's available, check it out. But nothing beats a proper profiling tool. All right, back to the topic at hand, parallelization. So when does parallelization become relevant? Of course, if you have a small model and a small input size, you're sort of in the bottom left half of this graph. And then a single GPU is fine, right? If you don't need the computational power to complete your training in a reasonable amount of time, there's no reason to go through the complexity of parallelization. Actually, in the hands-on session today, we'll work with a rather small model and a very small data. So you'll actually see that the benefit is quite limited. But it's just for illustration purposes, right? In a real scenario, you would only go parallel when either your model size is kind of big or your input size is kind of big, or maybe both. And then sort of at the top right, there's just a region that is computationally infeasible, right? We just need more powerful hardware to train these really extreme scale models or on very high resolutions. And where this boundary is between what you can still achieve with multiple GPUs and what is computationally infeasible very much depends on what system you're on, right? So if you're on a tier 2 system, a local university cluster, maybe you can use, you know, 1 or 2 nodes of GPUs, so maybe you have up to 8 GPUs. That line will be a lot lower. If you're on a tier 1 system, it will shift a little bit to the top right. And if you're on a tier 0 system, like one of the big Euro HPC systems, and you have thousands of GPUs that you can use for a single training, yeah, that's sort of the most that you can make of it. And then the real big commercial companies like the Metas of this world, they probably can go one step beyond, but this is what us mere mortals and researchers can achieve. All right, so back to the basics. What is parallel computing? Basically, parallel computing means that you're using multiple processors or computers to work on a single computational problem. In the context of AI, that typically means that you're using multiple GPUs, right? But some AI trainings work fine on CPUs. If you need an excessive amount of memory, maybe CPUs is even more efficient. So to understand parallel computing, let's have a look at serial computing first. Suppose that I want to do a very simple task. I have 4 images and I just want to apply some filter, like an Instagram filter to it. And I have 1 processor core. I could just do it one by one, right? That is serial computing. So I just process these images one by one, apply the filter and get my output. And it will take me sort of 4 unit of time steps in order to produce all of this output. If I have 4 processors available, it's pretty trivial, right? I can just say, okay, you know what? I'll actually have each processor do one of these images. So apply the filter to one of these 4 images. And I only need a single time step to produce all of the outputs. So yeah, that's pretty trivial, but that's the basics of parallel computing. And this is actually also called data parallelism. So here you're parallelizing by giving each processor a different part of your data, but basically you're making them do the same task, right? So the work that they do, this filter that they apply, is exactly the same for each processor. And that's called data parallel. Now the benefits of parallelization are clear, right? You get a speed up. But also you would be able to solve problems that don't fit a single memory. So that's not the data parallelism case. That's also more if you start splitting up the problem in smaller fractions as well and make each processor do a different part of the work. But then you could use multiple computers and therefore multiple memories in order to solve your problem. And that allows you to scale up your model to very large memory sizes. Of course, the requirements are that your problem should be divisible into smaller tasks. So how you divide this problem into smaller tasks is really the key to efficient parallelism. And some considerations for problem decomposition are like, how can I limit the need for communication, right? So where can I split my problem that I only need to communicate a little bit and not too much? And also the frequency of that communication is very important because every communication comes with a certain latency. And in the time it takes one computer to communicate to the other, you can do 1,000 operations on the CPU, right? There's really, networks are fast nowadays, but the CPU is still much, much faster. So how often you communicate and the amount that you communicate, you want to make sure that you partition your problem in a way that you limit both. The other thing to think about is how does that partitioning affect my memory consumption? So again, if your problem is that the model that you want to train is too big to fit a single GPU memory, you better pick a partitioning that makes sure that the amount of memory required is split evenly, right? So like if I have two GPUs and it would fit two GPU memories, I need to come up with a split that splits the memory requirement 50-50 or close to it. And then the final consideration is how does that partitioning affect my algorithm? So for example, the convergence behavior. And that is something, I mean, if you do data parallel training, I think I don't have a slide on it, but I'll try to come back to it sort of later on in the talk. The effective batch size that you're using will increase if you use thousands of GPUs, even if each GPU just sees a single data element, you already have a batch size of 1,000, right? So this might affect the convergence behavior of your training. And you need to account for it by adjusting your learning rate, for example. All right, so what types of parallelization exist? Well, there's a very, very long list here, but there's just a few that you have to worry about. So the first one is actually pretty easy. This is instruction level parallelism. That basically means that a processor can execute in a single instruction, it can execute like additions or multiplications on multiple data elements. So for example, it can add two entire vectors together in a single instruction, or even two entire matrices nowadays. That's actually what is called what the tensor cores on the NVIDIA GPUs are doing. So they're basically adding small matrices together in a single instruction. That type of parallelization is something that if you're a machine learning person, you typically don't have to worry about it because the framework does it for you. So PyTorch and TensorFlow, they know which low-level libraries to call in order to make sure that you're exploiting these special instruction sets that make this more efficient and that use this type of parallelism. So that's nice if you're from the machine learning world, right? Other people from the HPC world often need to work a bit harder for this. Then there's a class of parallelism that we call embarrassingly parallel, and this is basically where making your problem parallel is so trivial that we don't even think about it. So for example, if I would do a hyperparameter grid search, I'm basically training my model several times, right? So suppose that I say I want to try, I don't know, 3 different types of learning rates for a given model and a given data set. I can just start those 3 trainings independently on 3 different GPUs, right? And I wouldn't even think about it. But still, that's a form of parallelism, right? Because I can just do it at the same time. So if I have a bigger system, I can run more points in this grid search at the same time. But there is the key point is that there is no communication needed between these tasks because there is no dependency between them. Then there's data parallel. That's the topic of this session. So that's basically what I showed with the pictures, right? If I split my input data into multiple fragments and then make each of my processors work on a different subset of the data, that's called data parallelism. And then you have model parallel, hybrid data and model parallel, tensor parallel, and pipeline parallelism, which are basically covered in upcoming sessions of this course. So they are the more complex types of parallelism And that's also where you need to go if you have a model that exceeds your GPU memory, right? So data parallelism, you still have to be able to fit your entire model in the memory of a single GPU. If that doesn't fit, you're going to have to go to one of the other types of parallelism. All right, so how does data parallel work? And then in the context of machine learning, suppose that I have a batch of input images. I can split that input batch over, in this example, two processors. So for example, two GPUs that I have available. And each processor will hold an identical copy of the neural network that I want to train, right? So this also tells you that in terms of memory, you're not saving anything here, right? It needs to be able to fit in that processor's memory entirely. Each processor then does a forward pass, and it does a backward pass and calculates the gradients. Now, of course, because each processor saw a different part of that input batch, the gradients are not going to be the same, right? So each gradient is going to be different. And that's also where these processors will need to work together. So basically, what they do after the backwards pass and after calculating the gradients is communicate those gradients to each other and then compute the aggregate. So just sum them together. You could take the average, but in the end, that doesn't really matter because if you just adjust your learning rate, it's the same thing. So this is really how data parallel training works in deep learning. And then, of course, you need to do a model update. And for that, we then use this averaged gradient, right? So this model update, again, you multiply the average gradient with the learning rate. And this is also where you see that even if I just sum the gradients together rather than averaging, I would just adjust my learning rate accordingly. It's just a factor in there to get the same type of, the same scale of weight update that I want to achieve. And remember, because each of the models on the different processors was the same to begin with, so the W was the same initially, and the aggregated gradient, of course, is also the same. The learning rate is the same. So after the weight update, I also still have an identical model on each processor. Now, a little bit of a different view is a timeline view. Again, suppose that I have two processors working on the same problem. Here I call them workers. Yes, I see a question. Excellent.
Hey, I have a small question regarding the previous slide. Like when you mentioned that the model was still identical after the backward pass, but we started with splitting data objects into separate cores of the processor. So actually, I'm not sure if this is really true. And if it is true, then why, despite the fact that different data points were passed to each of the model items, and therefore gradient values were different?
Yeah, so the crux here, I'm sorry, I tried to explain it, but maybe I didn't do a very good job. So indeed, the gradients that are computed are different, right? So you have a Q1 and a Q2. Those are the two different gradients. But then there's a step in which these processors communicate their gradient to the other processor. And you calculate the sum. So you basically do the sum of Q1 and Q2 on each of the processors, and that sum is the same, right? So what you're doing is you're basically in an optimization, you're trying to determine which direction do I need to go in order to minimize my cost function, right? And each of those gradients is an estimator for where you need to go. And by averaging, you basically get a better estimator of where you need to go. And you're using that same averaged gradient in order to take a step in that optimization service. And that step is the same for both processor 1 and processor 2 because the sum is the same.
Okay, now I get it. Thank you.
Yeah.
I just forgot about. I just didn't notice the lower index when that it vanishes. So yeah, the gradient is the same.
Perfect. Okay. I see also a remark on the chat. When updating the weights, do we need to synchronize to make sure that all GPUs are updated at the same time? So actually, this is part of what PyTorch DDP does for you. So later down in the slides, I will actually show you how to do this in the code. But it's very simple. You basically wrap your serial model in a PyTorch DDP class. And that DDP class knows, okay, once I've done the backward pass, I need to do a weight synchronization. And I need to wait until all of the GPUs are finished in order to proceed. And that's actually also what my next slide shows. Things like PyTorch are very clever about this, right? So suppose that I have two processors, two GPUs working on this problem. First, they do a forward pass. That's the blue box. And then in green, you see the backwards pass. And of course, the backwards pass, it starts with the last layer of the model. So it's layer n, and then goes back to the beginning, right? N minus 1, n minus 2, etc. until it reaches the first layer and computes the gradient there, and then it's done. Now, the nice thing of things like PyTorch, and that's also my pro tip, is that like if you want to do parallelism in general, we always try to look for opportunities to overlap communication with computation, because that means that your hardware is not idling while waiting for communication, right? So you're trying to create as much overlap as you can. And that means send data as early as you can, right? So as soon as the gradient on the last layer has been computed, that data is known. So I can already start communicating that gradient to the other workers in the training. And that's actually what PyTorch does for you. So again, in AI, we're kind of spoiled because each of these frameworks, they're very well optimized and they abstract away all this complexity. They do this work for us, right? If you're in traditional HPC, you have to make a lot of effort to do this yourself, right? You have to program this yourself. But because deep learning is such a uniform task, all of these frameworks have already optimized this for us. What I also try to illustrate here is indeed the synchronization barrier. So that relates to the question on the chat, like, do you need to synchronize? Again, that is done by PyTorch itself. But yes, a synchronization needs to happen because all of those workers need to receive the model update from the other worker in order to compute the aggregated gradient, right? So this by definition gives you a synchronization barrier. And in this example, you see a little red box at the end, which is waiting time for the second GPU. I see a question. I'll come to you after I finish the slide. So you see a little box, the red waiting time. That's basically this worker was a little bit faster than the other one. There's always some random variation, right? So in the end, you'll have to wait for the slowest worker. And that also brings me to my second tip. Make sure that all your workers are equally fast. And there's only so much you can do about this, right? But the trivial thing is make sure that you use a single GPU model. Don't start mixing GPU models because you'll just be waiting for the slowest one. And then the rest is really up to your HPC center. Like if they have a proper system with proper cooling, all of those GPUs will in principle run at the same clock frequency and will be pretty much equally fast, right? Barring some very small fluctuations. If you have a little bit of a poor man's HPC system, you might start to notice that certain GPUs in the top of the rack are running hotter and therefore running at a lower clock speed because they have to throttle back their clock speed in order to not become too hot. And then you'll start to notice differences, right? So this is really also where you can differentiate between a good HPC system and a great one. Alain, yes.
Yes, so thank you for this presentation. In DTP, we can choose the parameter number of worker, but
Yes.
how it is the same that the worker here showed draw worker 1 and worker 2, and how we choose it this parameter?
So, that's a good question. I mean, typically you would choose the number of workers equal to the number of GPUs, right? Because in principle, if let's say a single worker has enough computational work to keep a GPU busy, then that's the most efficient that you can do. There might be scenarios if your model is relatively light, but you still want to speed it up because, I don't know, your data set is gigantic and you still want to get it done in reasonable time. Maybe there's a use case for scheduling multiple workers per GPU, but I would say that's very, very rare. Typically, it's 1-to-1. Does that make sense?
Thank you. Yes. Yeah.
Okay. All right, so now we're getting to the part where we're trying to look a little bit under the hood of PyTorch. How does it do all those things? So in order to aggregate the gradients, it needs to compute the sum of all of these individual gradients that have been computed, right? And this is what is known in the HPC world as an all-reduce operation. So what that means, like the all-reduce operation is defined as, okay, I have, for example, 4 processors in the beginning, each holding a certain data element, A, B, C, and D. And I want At the end of my operation, I want each of those processors to hold the sum of each of those elements. That's the definition of the all reduce operation. There's actually different variants, so you can have a different reductor operator. So if the sum is your reduction operator, this is how it's defined. You could also have a different definition, and then it looks slightly differently. But the one thing that this doesn't define is how to implement that operation, right? So how do you get the sum in the end at all of those processors? And there's different ways in which you can do this. The trivial way, and probably not the most efficient, but still the easiest to understand, would just be send all of the data to one of the processors. So for example, the processor number 0, and then add all of the data elements there, and then send the result back to each of your 4 processors. That will work, but it means that your first processor might easily become a bottleneck in this whole thing. So there are more efficient implementations of how to do this. Now, what does PyTorch use? Unfortunately, again, for us, it's abstracted away. So we don't need to worry about it as an end user, although you can tune these things. If you really go to very large trainings, you might want to play around with this. In principle, the communication backend that you select will determine the all reduce algorithm that will be used. And today there are 4 different types of communication backends in PyTorch. There's Glue, which uses a ring all reduce. I'm not going to go into the details because it's typically not so important for you to know exactly how these different implementations work. Again, if you come to extreme skills, you might want to play around with different options. Now, Nickel has a tree and a ring all reduce implementations, and Nickel is basically the communication library from NVIDIA, so it's really meant to be used with NVIDIA GPUs. And the nice thing with Nickel is it's smart enough to know what the connectivity of your GPUs is. So it knows, are there NVLinks between them? Are they all in the same nodes or are they in different nodes? And it will use that topology to determine what is the best algorithm to use in order to get this reduction done as quickly as possible. You can also use regular MPI. So MPI is the message passing interface. That's a standard type of communications library that we have in the HPC world. And then it's really up to the MPI library. So there's different types of MPI libraries, different flavors, and each of them might have a different default and different ways of setting other all reduce algorithms. And one that got added pretty recently is a backend called XCCL that's meant for Intel GPUs. And also there's a form of topology aware selection. So that's kind of the same as Nickel does. And actually that one has many options in terms of reduction operators. So a rule of thumb about which communication backend to use, because that is up to you as a user. If you're using an NVIDIA GPU host, use Nickel. If you're using Intel GPUs, use this XCCL backend. And then if you're one of the few people that actually train on CPUs, and there's nothing wrong with that, right? There are use cases just for training on pure CPU. It depends on whether you have InfiniBand or not. And if you have InfiniBand, whether you can do IP over that InfiniBand or not. If you can do IP over InfiniBand, use Glue. If you have InfiniBand but no IP over InfiniBand, use MPI, but then you have to build your PyTorch from sources. Good luck, it's not easy, but that's what they recommend. And then finally, if you have a CPU host and you have no InfiniBand, again, use Glue. So as I said, Nickel is actually aware of your topology, and I just want to show this to you. I have a terminal open. Let me just see if I can quickly get this to allocate a node for me. Is there a question? Yeah.
Yeah, sorry. Is there
You can quickly get a node. Yes. So if I run the NVIDIA SMI topo -m command, you will actually see the topology of this node. So you will see how the different GPUs are connected to the other GPUs. And in this case, there's NVLink of the 4th generation between each of the GPU pairs, right? So that's what this matrix tells you. And it even tells you how the GPUs are connected to the networking equipment. So some network cards are closer to certain GPUs than other network cards. That's basically what this is telling you. And this type of connectivity is something that Nickel is aware of. and can actually exploit, right? So it can decide, okay, apparently the connectivity between this set of 4 GPUs is very, very good. So maybe I first do an aggregate within that node, and then I send the data to another node, right? After it's been locally reduced, let's say. It could decide that, right? So this is the type of decision that Nickel optimizes for you. All right, back to the slide deck. I have to swap them again. Yeah, small intermezzo. So this is not really about parallelism, but it's kind of important to understand. PyTorch has a pretty complex call stack. So yes, PyTorch abstracts away a lot of this complexity from us, right? So the communication backend, okay, you set the communication backend and it takes care of all of the complexity. The distributed data parallel class, you wrap your model in that and it takes care of the communication. So that's very nice. But the downside of all of this abstraction is that stuff becomes sort of difficult to understand for you as a programmer, right? So you call a torch function, some layer, or you call the function to do a forward pass on a batch. And then that torch function calls other torch functions in the Python layer, which eventually call the C++ library from Torch, which eventually call the low-level libraries that are optimized for your particular hardware. So the good news is that these low-level libraries, like PyTorch knows which low-level library to use in which case, right? So you're training on GPUs, great, I'll use cuDNN or cuBLAS. You're training on Intel CPUs, great, I'll use MKL or MKLDNN to execute certain operations. And the nice thing is this, you don't have to think about it yourself and you get the benefit of these very well optimized libraries. But the curse is that it becomes less and less clear what is actually happening under the hood. But still, your choices matter. It's just very hard to see how. And this is from a post that I made a couple of years back. I made some investigation about, EfficientNet uses this thing called grouped convolution. It's a special type of convolution. The details are not so important, but the idea is that compared to a normal convolution, there is fewer floating point operations that need to be computed in a grouped convolution. Now, a regular convolution is basically, and I don't know, can you see my mouse actually? Can somebody speak up and tell me if you can see my mouse?
Yes.
Yeah, okay, perfect. So a normal convolution is basically all the way at the right here. So if I have 128 channels in a convolution and I have 128 channels in a group, I basically have one group that's a normal convolution. Same for the 64 case and the 32 case. The idea with group convolutions, again, is that you do fewer floating point operations. So that means less compute needs to be done in order to pass that layer. And that means, in turn, that you should be able to get more throughput, right? Less compute, it should execute faster. And you see this for the first couple of points, right? If I reduce the number of channels per group, so I go to more groups in this grouped convolution, you see the performance going up. And then suddenly, if I go to 4 channels per group, the performance completely tanks. It's terrible. It's divided by 4. From there, again, it goes up a little bit. And then suddenly it's quite good again. So what's happening here, right? And this is the complexity that's happening under the hood. If you actually start digging into this, this was on an Intel CPU, so it's using MKL in the backend. And you can actually run MKL in debug mode, and it will tell you which low-level kernels are being used. And in that way, I figured out, okay, for this sort of case where you have 1 channel per group, that's a very special case. It's called depth-wise convolution. That was probably pretty well optimized by MKL and by the PyTorch developers. So they made a proper routine for it that runs very well and very fast, and it uses AVX 512 based instructions on Intel CPU. So that's basically one of these vector instructions where entire vectors gets multiplied and added in a single instruction. And that gives you a very decent throughput. But then in between these two numbers, which were terrible in terms of performance, it was just falling back to a generic matrix multiply algorithm, so not an optimized one. And that's also why the performance was so bad. And then this part at the top here, that was basically, again, a properly optimized case, and it used a mix of AVX2 and AVX 512 instructions. So it's these kind of things. I just want to relay the message that this is, you don't expect this, right? As somebody creating a neural network, you don't think about, okay, how many channels per group should I use in order to execute efficiently in computational sense, right? You typically try to optimize this for what is the best model for the problem that I want to model, right? But your choices have an effect on how easy it is to compute the outcome. So be aware of that. It's pretty hard to find this stuff in the documentation. The good side is that NVIDIA actually has, like QDNN has pretty good documentation on this. Like they will give you hints like if you use multiples of, or if you use channel sizes 8, 16, 32, 64, whatever, this operation is very well optimized, right? And then you know, okay, if I use anything else, I might actually be killing my performance. So that might not be a great idea, even if in theory that model has a better capability of representing your problem, right? It might be cheaper to just add another layer with fewer channels and get the same representation capability than adding more channels in the same layer. So yeah, that's some food for thought. Again, you want to make sure that your serial case runs well before you start parallelizing, right? So this is another example of making sure it runs well. All right, let's see where we're at, 10:15. Yeah, I'll continue for a little bit longer and then I think we're up for a break. So data parallel versus distributed data parallel. In PyTorch, there's two types of classes that can give you data parallelism. The first is called data parallel, the second is called distributed data parallel. Data parallel basically uses a single process, but multiple threads. And that means it's also limited to a single machine because a single process always lives on a single machine. And actually this, in terms of parallelism, it's often slower than the distributed data parallel because you have to deal with what's called the Python global interpreter lock. So basically multiple threads in Python, they always have some kind of synchronization being done by this Python global interpreter lock. And another downside is that this class cannot be combined with model parallelism. So if you have a problem that you don't only need the speed up from data parallelism, but you also need to be able to use multiple memories, multiple GPU memories, you cannot easily do that with data parallel. The other class, distributed data parallel, there you basically use multiple processes. Each of those might be multi-threaded, for example, in order to do data loading. But in principle, there's one process per worker, so per GPU, let's say. And this also supports using multiple machines. So these processes don't necessarily need to live on the same machine, and they can still work together. And it can be combined with model parallelism. So here you can do this hybrid model and data parallelism. So yeah, I mean, bottom line, I personally don't see any reason to use the data parallel class. I guess this is how things started out in PyTorch. That's probably the first type of support that they implemented. But the distributed data parallel is really the way to go. Are there any questions? Let me bring this up again. There we go. All right. So now we really go into the how to get this done in PyTorch stuff. So the code level. And I've tried to also explain the why. Like, why do you need this section of code? Like, what does it really do in the background? And there are 6 steps to this, and we'll go into detail about each of these steps. So all in all, we need to do several things. We need to construct a process group that makes the different processes aware of each other and so that they can collaborate on a single trading task. Then we need to construct this distributed data parallel model. I already hinted at this, right? This is the part that takes care of the communication after the backwards pass. We need to distribute the input data. We need to send the data to the correct GPU. So if you have multiple processes running on a single machine, you want each of those to use one of the GPUs. We may need to alter the model saving checkpoint. This depends a little bit on what you want to do with that save checkpoint, as we'll discuss. And finally, we need to figure out how to actually run this code. So we need to do something with parallel launchers. Oh, by the way, before I forget, there was one question on the chat right before the break. So let me discuss that. The question was, does disabling the global interpreter lock in Python 3.14 resolve the performance problem? So that's the performance problem of the data parallel class compared to the distributed data parallel class. I also answered this in chat, but just to also have this on the recording, I would expect so. I haven't tried it myself, so you would really need to test or benchmark this. But even if it does, I would say the distributed data parallel class is still favorable because it supports multiple machines, and it also supports model parallelism, right? So, I mean, there's no point in, let's say, scaling up to a single node, and then you have to alter your code to use data parallel. And then when you figure out, okay, single node is not enough, I have to go across nodes, you have to alter your code again in order to use the distributed data parallel class. I honestly don't see the point. Like this, it's not like one is easier to implement than the other. As we'll see, actually, the amount of code changes that you need to do to use the distributed data parallel class are quite limited. So I think that's just the better way to go from the beginning. All right. That being said, let's dive into the first steps. And before we begin, I make a couple of assumptions in this tutorial. I assume that you're running on the Slurm cluster and that you pass the CPUs per task and tasks per node arguments. This makes sure that certain environment variables are set that will actually be reading in our code. If you're using a different type of scheduler, I mean, pretty much all schedulers set some of these equivalent variables, but the names might just be different, right? So then you have to figure out how does it map for my scheduler. Now, what is key is that each process in the distributed data parallel training is uniquely identified by its rank. So a rank is something that is commonly used in parallelization to make sure that basically you're running multiple times the same code, right? But you want each of those to do slightly different work. For example, to work on a different part of your input data set. And the way to achieve that is by using the rank, because that's a unique integer for each process. And there you can say, okay, this is, you know, I want rank 0 to do this part of the work, and I want rank 1 to do this part of the work. And that's also what we'll be doing with PyTorch DDP. In our case, so in this tutorial, we'll do pure distributed data parallel, so we don't combine with model parallelism, and that means that each rank, so each process, will use a single GPU. If you were to do model parallelism, then each rank could use multiple GPUs. We will use the concept of a local rank. So basically, the rank is sort of the worker ID in the total set of processes that you're launching, right? So if I suppose that I would launch on 8 GPUs across 2 nodes, I would have ranks 0, 1, 2, 3, 4, 5, and 7. But I would have local ranks 0, 1, 2, 3, 0, 1, 2, 3. So that's basically the local identifier of that process on the node. Again, this is something that's quite commonly done in parallel computing to have a local rank. And we can then actually use that local rank to determine, to bind a process to a certain GPU and make sure that we don't get 2 processes trying to compete for the same GPU. So we'll basically say each local rank just uses the GPU with the ID that matches their local rank, right? So local rank 0 will use GPU 0. All right, so the first step, constructing the process group. Why is this necessary? Well, as we'll see, we'll launch multiple processes with a parallel launcher. That's easy to do, but these processes somehow need to know about each other's existence to be able to communicate. And this is achieved by calling the init process group function. And this takes 2 arguments. It takes the rank and the world size. So basically, each process calls this function and says, hey, I'm rank number 0, I'm rank number 1, etc. And I'm part of the world size is basically the total number of ranks, right? So in our case, that would be, like in my example just now, it would be 8. And we can actually easily get those from the Slurm allocation. So this is where we start using these environment variables. We just read the Slurm end tasks from the environment. That's the total number of tasks that we've launched. So that would be, again, 8 in my previous example. And we'll get the Slurm proc ID, which is sort of the unique process identifier. So that's what we call the rank. And as you see here, the first argument that I pass is nickel. We've chosen to use nickel as a backend because that's a recommendation for NVIDIA GPUs, and the Leonardo system has NVIDIA GPUs. So that's what we'll be working with today. All right. There are different ways of calling this function, by the way, before I continue. There's different calling signatures for init process group, but this is the one that we'll use. Then there's a small piece of advice in the tutorial hidden somewhere, which says please call the set device function before calling the init process group, because otherwise you may get a hang. Okay. Indeterminate behavior, I don't know when it happens or when it doesn't happen, but it doesn't hurt, that's for sure. So it's good practice to just include that. And that's where we'll actually be using this local rank, right? So as I said, we'll try to pin each processor to the local to the GPU that matches the local rank. And then I've basically encapsulated this in a function because that's just easy to do, and it returns two numbers, the rank and the local rank of my current process. And then I can use it later on in the rest of my PyTorch code as well. That makes it easy. Now, the second step is to construct the distributed data parallel model. And that is surprisingly easy because the only thing that you need to do is actually wrap it in the DDP class. So basically you have your serial model that's called model in this example. I wrap it in the DDP class, and aside from the serial model, I have to pass which device IDs this model will be put on. Again, that will be my local rank because we assume each rank will use a single GPU. Why is this necessary? As I explained earlier, the backward pass, once it has been done on a layer, the gradient should be communicated between all of the ranks, and the special DDP class takes care of that, right? So right after having done the backward pass, there's a piece of code that says, okay, now just communicate my gradient to all of the other participating processes. Then the third step, distributing the input data. Of course, we don't want all of these processors to do exactly the same work, because then, what's the point doing duplicate work? We want each of them to see a different part of the data set. And that is also why we need to adapt our sampler. So there's something called the distributed sampler, and you basically pass that to the data loader class, the initialization. Calling signature, you can see it here. It's just distributed sampler, and you just pass it the training data set. So what this does is it makes sure that each of the processes taking part in this training sees a different part of the training set in each batch. And then there's again a little detail that we need to remember. Every epoch for this distributed sampler, we need to set a new seed. Otherwise, it would see the examples in the exact same order in every epoch, and that is typically not great for convergence. So typically, you want to set this seed at the beginning of the epoch. Easiest thing is just to set it to the epoch. That's always going to be different from the last iteration, right? So that's what we do here, but you could pick any pseudo-random initialization. Then we need to send the data to the correct GPU. Again, to determine what the correct GPU is, we use the local rank. So we send the data there and the target there. And that's pretty trivial, it's just a one-line change. Then there's this step about the model checkpoint. So one thing to remember is that we now wrapped our model in this DDP class. That means if you just call the model.stateDict, actually it contains your serial model, but it's it's prefixed with this module, with the module prefix basically. So now it's module dot and then whatever parameter name you had in your serial model. That's okay if you want to continue your parallel training later down the line, right? Because if you again continue a data parallel training, you will have a wrapped serial model. So this is the way to load it. But if you're saving your model checkpoint with the goal to then do inference, and you do inference maybe on a single GPU because it's lighter, then you probably want to strip the whole parallel part. So you want to strip basically this module prefix from all of the parameters that get saved. And you might do that at save time already by instead of calling model.stateDict, you call model.module.stateDict. Alternatively, you can actually also strip this prefix at load time, right? So it's not like if you chose one way or the other, it's not like you have to be stuck with it. You can still fix that. But it's just something to be aware of. And then running the code, of course, you want to spawn multiple processes, and there's multiple ways we can go about this. In this first example, I use srun as a parallel launcher. So that's the standard Slurm parallel launcher. And that means that for basically the init process group initialization expects two environment variables to be set already, which are the master address and the master port. The master address is just one of the nodes in your training, and the master port is just whatever. You can use a random port that's free. In this script, I just pseudo randomize a port based on the current job ID, and I picked as the master address just the address of the first node in my Slurm job node list. So this is basically an environment variable that contains all of the nodes involved in the current Slurm job, and just by picking the first one, that's always good, right? Even if I just use a single node. And this basically tells the initialization method, contact this node first on this port number in order to figure out, what are all the other processes, right? So that's kind of orchestrating the whole thing. Alternatively, there's Torch Run as a parallel launcher. So this comes with PyTorch. It works slightly differently in that it expects different things to be set. So it doesn't need this master address or master port number, but it actually needs various command line arguments, which are in the end kind of similar, right? Because whenever you start such a training, you need to have one point that orchestrates this whole thing. And also here they have what they call the rendezvous endpoint. That is basically the node that does this orchestration. Again, you pass it a port number. I hard-coded it here, but it's neater if you pseudo randomize this, right? And it's even neater if you figure out first, is this port actually free, right? You can do that in the shell as well. And then for Torch Run, you can actually pass a rendezvous ID. So that gives it a unique identifier. So even using the same node with the same port, you could orchestrate multiple parallel trainings if you wanted to, as long as you give them different IDs. I don't know. I mean, in a regular HPC context, I don't see that happening, but maybe on cloud nodes, that's more normal. So again, to get the head node IP, I just run the host name on, this is in the batch script, right? So if I run host name, I just get the host name of the current host. I get the IP address. That's what I store in the environment variable. And that's what I then pass as an argument here. The other thing that Torch Run takes is number of processes per node. So in this example, I'm trying to run 8 processes across 2 nodes. So that's basically using 8 GPUs. So I'm telling Torch Run launch 4 processes per nodes, and this whole thing is going to run on 2 nodes. But be aware, Torch Run is it doesn't integrate with Slurm. So it's not aware of any of the other nodes that Slurm allocated. So it can only launch processes on the local node. And that's also why, again, this is wrapped in another srun command. And now the srun command actually starts 2 tasks with 1 task per node. So what this does is it will actually start a torch run command once on each node. And then the torch run command starts 4 Python processes. So it's like a nested thing. There's some small modifications that you actually need to make to the code in order to use this, because the environment variables that Torch Run specifies are slightly different from the ones that Slurm specifies. But again, the goal is then to get your rank and your local rank so that you can use this information to tell your process to use the GPU with your local rank, right? So that logic is unchanged. It's just the environment variables that change the names. And you might be wondering, why do I want to do this complex? Yeah, so this is actually reflecting that change, right? So instead of reading the Slurm environment variables, local rank is now just the name of the environment variable. And also there's a rank environment variable name. And you actually don't need to pass these to the init process group anymore if you use Torch Run, because the init process group is just it's aware of this already. We still return it from the DDP setup function because we use it later on in the code to then move the data to the correct GPU. In theory, you can use any parallel launcher that you want, right? You could even use MPI runs as long as you modify this DDP setup to get to figure out your local rank and your global rank in a unique way. Which one to use, that really depends on your personal preference and your needs. I would say the advantage of SRun is that there's less abstraction, so it's probably easier for your HPC side to help you out if you just present them with a batch script that's based on SRun. They know what's happening, even if they don't know PyTorch specifically. If you use TorchRun, there's a little bit more abstraction, but also more functionality. So TorchRun actually has functionality to automatically restart if a single rank fails. So there's more resilience in that. Whereas if you would use the pure SRun approach, you would have to manually resubmit a new job and restart from a checkpoint. But if you use TorchRun, it's probably easier for the Torch community to help you than your HPC side. A little word of warning, and this is something that I don't quite understand, but I've tried both. And you can actually try both as well because I have the code available in the GitHub repository. I saw a performance decrease when using TorchRun compared to SRun. I don't fully understand why, but again, this is the downside of having more abstraction, right? So stuff happens that you don't really have full control over. I don't know. Something is happening that's causing the performance to decrease. And maybe if I spend time with this, I can figure it out and that it's just equally good, but just to be aware. All right, and that actually brings us to the material, so the hands-on. I have a couple of exercises. My idea is that we'll just read through them first. I will read them out, like tell you what the goal of the exercise is. There's a couple of bonus exercises as well, depending on how fast you are. And my idea is to just give you time to work on this yourself. I think initially, let's say maybe 45 minutes to an hour or something at most. But I'll also maybe do a query on the chat at some point, like, are you done? How far are you? Do you need more time? And then try to figure out where we are because, yeah, if everybody's done, there's no point in waiting. And then at the end, I want to do a recap. So basically, I want to go through the code altogether to show you what I've changed. And mind you, so the material is on the GitHub. Actually, the answers are also there. So yeah, if you want, you can take a sneak peek at the answers as well. But I would encourage you to first try it yourself and see how far you get. And of course, feel free to ask questions in between if you can't figure it out. All right, that being said, the first exercise, you will find the serial code msclassify.py in the training material. And the first thing to do is just create an interactive allocation with slog. That means that your shell will still be on the login node, right? But if you launch something with srun, that will actually be launched on the batch node. So that will be launched on a node that has the GPUs. We'll be using the standard Chinica AI module here for convenience. I mean, you can make your own PyTorch installation if you want to do that. Fine by me as well. But this should just run with the standard Chinica AI module. And the way to launch it, so here, of course, this is still a single process, right? The only reason we started with srun is because we wanted to run on the batch node. So I'll tell it I want to run one process, Python, msclassify. I'll specify batch size, a number of epochs, and the data directory. So I already staged the data for this. That's basically the MNIST dataset, very famous small dataset for that's being used in trainings. The nice thing, because it's so small, it's also very fast to actually train a network on it. And that's located here in the fast/data directory. So if you just pass that as arguments, it should just work for everybody. If not, let me know. Then the second exercise is basically to take the serial run and make it parallel, right? So adapt the script. That's also why I put an arbitrary script name in here. So just copy it, start making modifications, and go through these 6 steps that I just explained. I'm seeing a question, will the examples work with PyTorch 2.5.1? I expect so. Because like the Chinica AI one is older than that, and I think I also tried it with a virtual environment that had one that was a lot newer than that. So I'd be surprised if it doesn't work with PyTorch 2.5.1. Give it a try, let me know if it doesn't work. We can see if we can figure it out on the fly. Another question, if I want to run this code in the cloud, should I use Torch Run version of the code, as I do not have access to Leonardo cluster? So yeah, if your cloud node does not have Slurm setup, and I assume that it doesn't, then Torch Run is indeed the way to go. Yeah, then yeah, that's the easiest. Yeah. So 2 hints, don't forget to set the master address and the master port number in your batch script, or in your environment, sorry. So now we're still doing this interactively, right? So set this in your environment first before you run the srun command. And try to get some code timings in there just to be able to compare what the speed is of the serial code versus the parallel code. So, and a hint there is make sure that you add a dist.barrier function right before you invoke the time.time invocation. So if you're timing parallel code, of course each of the processes could be running at a slightly different speed, right? You want to make sure that they really reached a certain point. You would never do this in a production run, right? Because every barrier that you call can slow down your code. But when you're instrumenting your code, so when you're trying to figure out how fast does this section run, then it can actually be very helpful. So yeah, I encourage you to do that. Just, I don't know, put a single epoch, try to time a single epoch for the serial case and the parallel case, and see how much speed up you get. And then try to decide for yourself, is this enough to justify using 2 times more resources in terms of hardware or not? Then a bonus exercise. So this was all still interactive allocation. Here for the bonus exercise, please release your interactive allocation first because we only have a limited size reservation. So you just, after your slloc, you do your things, then you just type exit and it will release your interactive allocation. And then create a job script for your 2 GPU run. So just try to replicate what you did interactively, but then put it in a job script. And once that completes successfully, try to scale up to 4 and 8 GPUs. So for 8 GPUs, you'll actually have to use 2 nodes. We have fewer nodes than students, so the only way that this works is if people really release their interactive allocation, right? And then we get more and more space, and the jobs will just be scheduled one behind the other. They're very short, so the training takes, I don't know, half a minute or something. So it should be pretty quick to finish. And then try to determine what is called the strong scaling speedup and the efficiency. So I have pasted 2 links here where you can read up on what strong scaling means and what efficiency means. And try to create a scaling plot out of this and see how that looks. So that's bonus exercise number 1. And then the other one, okay, if you're not already on a cloud system, then you have to use Torch Run, right? But if you're on an HPC system, just give it a try. Try to also use Torch Run. Modify your batch script, modify your Python code. Again, make a copy so that you can retain the other one as well. And then see if you can make it run with Torch Run as well. Let me see. Oh yeah, one thing to remember, if you want to use Torch Run, you have to set the OMP num threads. Otherwise, it will just use 1 thread, and that will definitely tank your performance. And as I showed in the slide, if you want to use Torch Run on multiple nodes, you'll need to wrap it in an srun statement. So if you do single node, you can just do Torch Run. But if you want to do it across nodes, you'll need to use srun in order to make sure that 1 Torch Run command is being run per node. And then see how much performance you get, and if you can actually get my same issue with the performance as compared to the srun approach. I see one more question. What requirements files should I use if I need to create my own environment on my HPC? Honestly, I think the only 2 things that I installed were Torch and Torch Vision. So if you have those 2, I think it should work. If not, send me the error that you're getting and I'll try to figure out what's missing. All right. And then there's a final bonus exercise. With Nickel, you can actually change those all reduction algorithms, right? So I here linked a page from the documentation where you see all of the different algorithms available and how you can set an environment variable called Nickel algo to switch between the different ones. And then try to see if you can spot any performance difference. And I would do this at the largest scale, so 8 GPUs, because any smaller scale, you'll definitely not see it. All right, and I think that's it. And yeah, so once you're done, I'll check in the chat how far people are. At some point, we'll start doing a recap and we'll go through it together. First exercise. Wait a second. Yeah. So first exercise was just to run interactively the serial code, right? So that's basically, well, always a good starting point, get your serial stuff to run first. I saw one of the issues that was reported. If you actually copy and paste from the slides, there's this annoying thing that this is a slightly different dash than it should be. So that will give you something like syntax error. If you then manually type the dash, it's resolved. I don't know, it's just annoying, but that's how it is. All right, let's just do that and show you what it looks like. So what you should have gotten, I'll take a fresh terminal. What you should have gotten is the following. First, we create an allocation. That takes a little bit of time for the job scheduler. There we are. And then we load the modules to make sure that you're in a clean module environment. Like in my case, I don't, well, okay, there's some default modules loaded, so okay, you can purge those as well and start completely clean. There we are. And now I can actually run the serial code. And see, I have this, the GitHub repository cloned. So I'll run, yeah, that's where the job script is, or the Python script is. As I said, you'll have to replace this dash because it's the wrong type of dash. And now after a small startup delay, you should see it starting to run over the epoch. So now we asked it to do 5 epochs. I don't know if you noticed real quickly, but the first epoch, if I scroll back, you actually see that it's a little bit slower, right? The first time there's always some initialization overhead, buffers being initialized, etc. So whenever you time any code, make sure that you run multiple, well, at least multiple iterations, but probably also multiple epochs if your dataset is not too big. And here we see that we get about 47,000 images per second if we calculate it. All right, so that's already quite a lot, right? Because this whole data set, I'm not sure exactly how many images are in it, but I think a single epoch here, it takes 1.25 seconds, so must be something like 60K images. Normally, this is not something that you would start parallelizing, right? It's fine to wait for a second, and it's also fine to do 100 epochs like this, and already, if you look at the accuracy, this thing has pretty much converged already. That's because it's a toy data set, it's a toy network, right? It's tiny. But in any real world scenario, if you take a heavier model and some heavier input data, yeah, that's when it starts to become interesting. But the nice thing is that this allows us very quick experimentation. So yeah, the second exercise was to actually make this data parallel, right? So we'll actually run the data parallel script. I already have it here. And I will show you first the key changes that I made to make this data parallel. So basically every change, I marked it with this DDP, this DDP command. So as we discussed in the slide, step 1 is basically to set up the process group. So I defined this DDP setup function, which in the end returns a rank and a local rank. Again, I'm on the Slurm system, so I'll query the Slurm environment variables to get the world size and the rank. Number of tasks per node, I can also get that from the Slurm environment. I realized that I actually did not put that on the, I'm not sure if I use this. No, I don't think we use this. And then the local rank, you can just get it from the Slurm local ID. Here we call the set device function as was recommended in the official PyTorch tutorial, and then we call the initialize process group. And here I just print some output just for my own sake. It's nice to have some reporting that you can see, which nodes were assigned to this thing. So everyone prints their own host name, and it also allows you to see how were the different ranks mapped over the different nodes. So that's just a nice to have. This is also something I did not discuss in the slides, but it's actually good practice to destroy the process group once you're done with it. I think the really the only case where this would be needed is if you do several distributed trainings in a single Python script. That would be quite awkward to me. Like I would just separate that over different Python scripts, but I guess in theory you could do it. I don't think anything really goes wrong if you don't destroy the process group, but it's a neat way to do it. Well, nothing basically changed here up until calling the DDP setup function, right? We created the function, now we need to do something with it. So we call it and we get the rank and the local rank back. And this thing actually also calls the init process group function. So that's taken care of after this stage. Then from step 3, we needed to use the distribute sampler to make sure that every rank is doing a different part of the dataset, right? It's training on a different part of the dataset. So that's being done here with the sampler equals distributed sampler argument. That's the only replacement I made. Then comes the model. Of course, this needs to be sent to the correct GPU. Now we use the local rank. I think before it said something like GPU ID. So basically everything that said GPU ID, we just replace it with the local rank. And we need to wrap the distributed data parallel model, or the serial model in the distributed data parallel class. And again, pass it the local rank as the device ID on which this model will be stored. And of course, for the optimizer, first initially we passed the serial model. Of course, now we need to pass the DDP model to it. By the way, if there are any questions, feel free to interrupt me. If something is unclear, then please interrupt me. So before the timing code would just have this time.time. Now I introduced a barrier to make sure that all of the workers would reach this point before starting the timer. Otherwise you get strange things like if the initialization on one rank took a lot longer than on another rank, yeah, your first timing might be off. From step 3, that was about the distributed sampler, right? The instruction was also to call the set epoch function every time an epoch starts, so as to initialize the sampler to give it a different, like the dataset in a different order every epoch. So that's what we do over here. The train function, essentially nothing changed except that I replaced the GPU ID with local rank. And again, before I call the timing code, again, I introduce a barrier to make sure that all of this stuff has finished, right? So the train function has completely returned all of the work that the train function issued on the GPU was finished, and all of the communication work also finished. So that means it will have communicated the gradients, and it will have done a model update by the time it reaches, or by the time it finishes the barrier. And then I can actually call the timing code again. Now this is just a little trick to make it easier to read. If you don't do this, then you might get some like different ranks are printing to the same output file, right? So the order of things might be a little bit off. So again, I flush the output buffers and I call another barrier. That's a small detail. It won't affect like how your training is happening, right? And then we print in a nicely formatted way, like how much time did it train for this epoch, like how much time did it take to train this epoch, and how much throughput do you then get per worker. I think that this is actually, let me see. Yeah, and then of course, the total throughput is just that number multiplied by the number of workers, right? So that's what we get here. And the total throughput is in the end the thing that's relevant if you want to determine how much can I speed up my run. Now there was a question on the chat. Somebody came up with a scaling graph that looked a little bit odd because they timed the full execution of the code, including all the startup. And this code, it must be said, this is toy code, right? So the initialization time is relatively long compared to the actual compute time. For any real use case, it will be the other way around, right? That will definitely be dominated by the training code itself. So basically the for loop that loops over the epochs. And then the easiest way to get rid of your initialization overhead is just to time that small section within the epoch loop. And that in the end, for your production run, will determine your total compute time as well. For the model saving, I actually did not alter it. I just said, okay, I'll save the state dict as is for the DDP model. So in this way, if you wanted to continue training with distributed data parallel, you could just call the load function again, and immediately you have a DDP class model available. And this cleanup function is that cleanup of the process group. So all in all, I think the amount of code changes that you need to make in order to go from serial code to distributed code are very minimal in case of data parallel training, right? So that's also the nice thing about data parallelism, that it's relatively easy to implement. Yet it gives you a decent speed up, right? So if the timing is if the time to train is the problem, then this is a very nice solution. All right. I don't know if you've seen this, but I also prepared some job script here in the Leonardo subfolder. So here I basically had a job script that shows you how to set the master address and the master port, and then use srun to call this DTP training script. And that was basically something that you could just submit and it would work. Except that I commented the reservation name because I didn't know what it was going to be. So that's the only thing that you would then have to change. All right. So that was basically exercise number 2. How much speed up did you see? I actually ran it a couple of times, put it in a small Excel spreadsheet. Let me see if I can make it a little bit bigger for screen. I guess if you ran this on 2 GPUs on Leonardo, you should have gotten something like 63, 64,000 images per second. So yeah, it speeds up, but not by a factor of 2, right? So if you compute what the efficiency, it's something like 70%. It's not terrible, but it's not great either. And that's because this is a toy example, right? There's no point in trying to speed this up because it's already very small. Again, if you have a much bigger network, much larger training data, higher resolution images, etc., then you would probably be much closer to an efficiency of 1, ideally. And then the question, like, is it worth it? I think in this case it's not, right? Because you could easily train on a single GPU and get the job done within a reasonable amount of time, right? Even if I wanted to run 100 epochs, it would only take me, well, if it's 1 second per epoch, it would only take me 100 seconds. There's no point in trying to speed that up. But if your code takes, 5 days to train, then maybe it's nice to be able to speed it up because it will allow you also to explore more hyperparameters, etc. And beyond that, I also ran on 4 and 8 GPUs, and you see that basically the amount of performance that you get extra, it reduces every time, right? So here we got about, what was it, 18K? Well, so this is not too bad, 18K, 20K extra, and another 20K. Okay, so it scales, beyond the original overhead that you pay for having the communication, it's not so bad. If you make a graph out of it and you check the theoretical throughput against the actual throughput that you're getting, right? So this is just multiplying by 2 every time, you see it starts to bend off, and that's basically showing, okay, the communication overhead is kind of keeping me from achieving this, the performance that just, theoretically should just double. I hear a question beep. Let me see where it is. Can I share the Excel with you? Yes, I can. I didn't even save it locally. I just made it on the fly while you were working as well, but I will paste it in the course materials channel once I save it. All right, so basically I also already covered this, right? So try a scaling run, make a job script out of it. I just showed that to you. And then just submit it several times and create a scaling graph. Mine is not a very proper scaling graph, but I just made it on the fly very quickly. Try things with torch run. So how does that alter things? If we look first again at the Python script, that is this one. I hear another bleep. I need to find it. Right. And then the job script for this one looks a little bit different. That's the torch run batch job. Here you see so this is a small one, so I only did it on 1 node. I launched 1 task per node, so I still wrapped it in an srun, but I didn't really need to. If you would scale this up to 2 nodes, this would just say 2 nodes, 1 task per node. And then the amount of processes per node. In this case, I reserve 2 GPUs. So I tell Torch Run I want to run 2 processes per node on one node. And the rendezvous port, again, here I set it sort of pseudo randomly. And let me see, where's the head node IP? That's here. I get the IP address from the host that is actually executing the batch script, right? So even if you allocate 2 nodes, there's always one host that will execute this batch script. And only when you do an srun will the other node also be involved, right? So this will basically give you a single IP, and that gets passed here as the rendezvous endpoint IP. Again, a question. So basically, it's the best practice to allocate 2 nodes with 4 GPUs if available and avoid 4 nodes with 2 GPUs due to unpredictable behavior. Yes. So assuming that you're on a system that has 4 GPUs per node, right? This can also vary. Some systems have 8 GPUs per node. But assuming that you're on a system with 4 GPUs per node, it's better to use 2 nodes with 4 GPUs to get to 80 GPUs rather than 4 half nodes with 2 GPUs each. Because then indeed you're sharing with somebody else and they might, at unpredictable time points, stress the interconnect that you're sharing, stress the memory bandwidth that you're sharing. Like CPU cores and GPUs are dedicated, right? They're part of your C group, so only you can use them and the other person on that node cannot use them. But things like memory bandwidth and network bandwidth cannot be hard partitioned, so those are shared. And then it's indeed better to have an exclusive node. All right. Wait. Oh, I guess I had a job script still running here, or an interactive job. That's fine. So this is basically the call signature then. I do torch run, number of processes per node, rendezvous port, the endpoint, the head node IP, and the port. And I invoke this adapted script, right, which reads the different environment variable names. The rest I keep the same. And if I look at the output of these, I can just query one of my, I ran this last week somewhere. So for example, the DDP one, let me check the last one that I ran. I indeed got something like 63,000 images per second. And if I check the torch run one, 3, 2, 8, 9, I somehow got a lower performance, only 53K. So yeah, that's about, what is it, 15-20% lower performance than I got with the srun setup. Again, I'm not entirely sure why. Like I would need to dig into this, but this is the downside of this extra abstraction that torch run gives you. Maybe I'm curious, are there other people who saw other things when they used torch run, like and compared it to srun? Were there other people who came to a different conclusion? Or did everybody see this worse performance with torch run? And just recap the steps that we took. Step 1, constructing the process group. This was necessary to make sure that all the processes can work together. Step 2 was constructing the DDP model, and that's needed to make sure that PyTorch automatically aggregates all the gradients before it does a model update. Step 3 was distributing the input data. That's needed to make sure that each of the workers sees a different part of the data, because we want them to do different work. Step 4 was to set the data to the correct GPU. So it's basically replacing all of those GPU IDs with the local rank. And we need this, of course, we want to make sure the data goes to the same GPU as our model. Step 5 was optional. That's altering the model saving checkpoint if you want, depending on whether you want to store the actual DDP class model or the serial model that is wrapped in the DDP class. And then finally, to run the code, we needed to spawn multiple processes, and we experimented with 2 different parallel launchers. Again, MPI run would definitely also be an option. So there was this question on the chat, right? Like, what do I do if I'm not on a Swarm system? Actually, if your system does not have Swarm, but it does have an MPI installed, you could use MPI run. NPI run also sets a rank and a local rank. I'm not entirely sure what the environment variables are called, and it might actually depend on the NPI flavor that you're using, but that could definitely be sort of a neutral alternative that's not really tied to an HPC system. So by now, you should understand what data parallel trading is and how to specifically use the PyTorch Distributed Data Parallel class, and hopefully also a little bit about what PyTorch DDP does under the hood. For further reading, like if you want to become a real expert, there's this very, very extensive page on Hugging Face about how to scale LLMs to sort of the biggest scales that they are run on, tens of thousands of GPUs. That covers all the types of parallelism, so much more than we covered here in this presentation. But it's a nice reference to have if you want to dig deeper into this topic. All right, with that, I would like to thank everyone for your attention. We still have 20 minutes until 1, so I'll just stick around. If you want to play around more and you have more questions, then I'll be here. I can contact you on the chat, but I'll also stay in the meeting if you want to speak up. If not, feel free to go for an early lunch, and good luck this afternoon. Thanks again.
I'm back. Gyula, are you with us?
Yes, I'm here.
Perfect. Welcome. And I will just give a short introduction, as I did in the morning. And that, yes, today the afternoon session will be led by our NCC trainer from NCC Hungary, Gyula Ujlaki, and he will be speaking about model parallelism with PyTorch. So, Gyula, the floor is yours, and you can start.
Thank you. Let me share my screen. All right, now you should see it.
Yes, I can see it. Perfect, we can see the full screen. Perfect.
We are starting with the thank you. We are not at that part yet. So good afternoon, everyone. I'm Gyula Ujlaki, and I work at NCC Hungary. And my task there is to have the users on the Commodore supercomputer to run AI models, or more precisely, deep learning jobs. Today I am going to talk about model parallelism with PyTorch. So we are going to continue the PyTorch Casper already started in the morning session, but it's in a different perspective. So let's first start with why do we need model parallelism? Nowadays, the large language models are pretty popular, and they are very large compared to a GPU memory. For example, if we have a Llama 70B model that for training that needs about 13 or 12 GPUs. If we think about NVIDIA A140 gigabyte GPUs, of course, there are larger and smaller models, but basically these techniques, the model parallelism techniques, will help you distribute this model or divide this model among the workers in the cluster. And let's start with the calculations, how much memory a model not usually, but in this specific case, how much Llama 70B model needs in terms of GPU memory. For inference, I hope you see my cursor. let's see. So in inference, on the left side, on the top, you see we need to calculate with the precision. By precision, I mean FP16, FP32, and so on and so on. Usually for Llama 70B, it's FP16 or FP8. And we need to multiply this number with the number of parameters and divide it by 8 if we want to get the memory requirements for our model. Then, of course, we need to calculate the memory overhead. Sometimes, even if you calculate perfectly the model size, you still can encounter out of memory errors. So that's why for safety concerns, usually a 20% of overhead should be added for that requirement. This was only the inference part. So if you want to run the model in inference mode, then you need to calculate with the precision and the number of parameters, and that's it. But for training, it's a different case. More so because during the training, you can use different optimizers. As you see here, you may in the two most popular cases, you use an NMB optimizer or an SGD optimizer with a large language model, and both optimizers you use a different. They need a different memory size for storing the states. So for NMB optimizer, it is 4 times the memory requirement of the model, like this here. So we need to multiply the memory requirements for the inference and then add the optimizer state requirements to it. Then we need to calculate with the gradients as well. So we need to add another memory model memory requirement to that. And of course, there are the activations, and these activations also should be stored during the training, of which I'm not going to go too much into the detail because it depends on the application how you calculate these activations. It is just for an informative purpose. So let's calculate the actual Llama 70B model here in FP16 precision, just so you can see an actual example for that. So 70 billion times the FP16 divided by 8, as I've said before here. That's 2 bytes for each parameter. So 70 billion times 2 equals 140 billion bytes. Then we add the optimizer states to it. That results in 560 billion bytes. Then we add the gradient requirements. So we end up with 700 billion bytes for the Llama 70B model. And converting this number back to gigabytes means approximately 652 gigabytes is needed to run to train the Llama 70B model. And this calculation is not so far off compared to the official recommendations that can be found here under the site. And it depends on the specifications, of course, how much memory you need to run, you need to train your model. So that is the justification for why do we need model parallelism at all. Because compared to the GPU memory sizes, on the Leonardo supercomputer, you have a NVIDIA A100 GPUs with 64 gigabytes of memory. 500 gigabytes cannot be put onto those GPUs, at least not in FP60 mode. All right, and I am going to talk more about layer-wise model parallelism, and we will see the layer-wise model parallelism techniques in practice as well. So this layer-wise model parallelism is useful if you have multiple devices in your machine. And I purposefully said devices because it doesn't necessarily mean that you have GPUs. For example, you can offload some of the layers to the CPU as well. I'm going to talk about that a bit later. Or if you have two GPU devices, you can divide the layers evenly between the two GPUs. Or if you have four, you can divide it to 4 GPUs as well. But you need to keep in mind that layer-wise model parallelism equals to multiplying the GPU's memory size. And this means that the performance of the model is not going to increase if you increase the number of devices, only the memory size. Furthermore, it's not only not increase, but will decrease the performance if you, for example, run the model on 2 GPUs because of the communication overhead. And the communication overhead, it really depends on the interconnect between the workers. So if you have, for example, NVLink between the workers, then the communication overhead is smaller than if you would have only PCIe connection between the workers, like in the case of CPU offloading. But we are not talking about radical overheads. So we are not talking about minutes or hours. We are talking about a small fraction of the original training time if you would have run the model on 1 GPU. Comparing that to the 2 GPU setup, for example, gives you 5 to 10% overhead or even less than that if you have NVLink connection between those GPUs. I also need to tell you that model parallelism is not only suitable for one node setup, but PyTorch will allow you to run the model on multiple nodes as well. But for that, you need to get familiar with remote procedure calls, which is not an easy task to do in PyTorch. We are not going to see any exercises for that because between the PyTorch versions on our supercomputer and PyTorch on the Leonardo supercomputer, it's different, and I weren't able to properly port the code here. So I'm not going to show you any bugs on the supercomputer. That's why this remote procedure calls is going to be left outside the exercise. However, the remote procedure calls documentation will also is also having a note that this RPC package is still in experimental phase, so it's going to undergo changes in later versions, or maybe it already taken its final form. I don't know yet. But just leave it at the side. You should know that RPC, if you want to increase the number of workers between the nodes and you want to distribute your model between the nodes, remote procedure calls or RPC is the thing you need to get familiar with. Okay. When it is useful, the layer-wise model parallel strategy. Of course, the obvious case is when your model size is very large compared to the GPU memory, and you need to distribute it among the workers. But I've told you before that is going to be underperforming compared to the one worker setup. If your model is slightly larger than one GPU, then you can offload some of the layers to the CPU, and then it's going to be a bit slower than optimal, but you will not sacrifice that much performance compared to the one worker, one GPU setup. So that is a use case for layer-wise model parallelism as well. If you apply pipeline parallel logic, we are not going to do any pipeline parallel logic in this session because it is going to be shown you in the later sessions, but you need to know that pipeline parallelism is it's based on layer-wise model parallelism, although it has undergone significant changes during the development of PyTorch and Lightning or DeepSpeed as well. But if you do a pipeline parallel logic, then layer-wise model parallelism is useful as well. And then the last case, if you have a large model that should be distributed among the workers, like one layer is so huge that you need to put that layer into a GPU, and then you have an even larger layer that needs to be parallelized in an interlayer way. This is called tensor parallelism. Then you need to combine these techniques just to fit the model into the GPUs and somehow run it. And lastly, RVMP can be combined with other parallelism techniques as well. For example, in the previous session, you have seen the DDP, and I wrote it here that inefficiency is upscaled. What I mean by that, if you have a 2x2 setup, like you distribute your model between two GPUs, then you can multiply this and upscale it to 4 GPUs. Those GPUs are going to work in pairs, but you are not just multiplying the performance, but you also multiplying the inefficiencies as well. But we will see an example for that. All right. How is it looking in practice? And it is really pretty easy to write a code like this. What you need to pay attention in PyTorch is that you need to use the proper device ordinals so you don't mess up your pipeline. And then it's not really a pipeline, but let's call it a pipeline now, because the first layers of the model should be, in this example, should be put to 0. But the very first layer will expect the input. So in our case, will be images, the MNIST dataset. The input should be also put to 0. During the forward passing, each last layer on the device will produce an output that should be forwarded to the next device in line. So the layer 3 expects expects layer 2 output, and layer 3, so layer 2 output should be forwarded during the forward method and should be put to CUDA1, and so on and so on and so on. And lastly, there is going to be a loss here at the last step on the third CUDA3 or the forward device, and this last layer expects the labels to be on CUDA3 as well. So here, if you don't put the labels on CUDA3, then you cannot run a proper layer-wise model parallelism. PyTorch will give you back an error, and you need to debug the code. During the forward pass, you need to properly pass forward the outputs of these layers. So you need to put the proper device ordinals in your code. But in the backward pass, you don't need to define anything. PyTorch will automatically do it, the backward pass, in a reverse order than it was the forward pass. And then after the gradients have been created on devices, the gradients and the model, sorry, I just have to put my, sorry, there's a bar that disturbed my view. So after the gradients have been created, the PyTorch will update the parameters parallel on each device. We will see this in practice because we will trace the tensors and we will trace the operations during the training. And since I am not much of a talker first, and I think it's better to show it in practice, let's go forward with the practice part. Okay, and I am going to show you what to do here. Just a moment, because I need to change the screen. Okay. You will find the exercises in the work folder under is it not going to log in? Well, I cannot access Leonardo, and until that point, I'm going to read the question if there is any. Does any of you have problems logging in to the Leonardo, or is it only me?
I can log in.
And it's only me. Oh, sorry. My bad. Yeah. Since I don't really like doing everything during the login sessions, I just automatize the login a bit. Yes, it should work. Okay. I'm going to increase the size here as well. No. Later. So you will you will see the prepared exercises here. Under this this library, and mine is already in my home folder, but you should copy the exercises for yourself on your home folder. And first of all,
excuse me, can I ask a question, please?
yes.
How about those who don't have access to the machines? How can we do those exercises?
It is already uploaded on the GitHub.
Okay, cool. Perfect. Thank you.
I did it an hour ago, so it wasn't visible before. And first of all, we need the NoMP. This means no model parallelism. And I'm going to walk you through the code, because there are some changes compared to a conventional training. So as I told you before, this is just a fully connected model. I haven't told you before, but this is a fully connected model. This is only for practice purposes. It's not going to be performing very well. We are going to classify the MNIST dataset. And what you need here in your code is the profiler line. Actually, we don't need we need the data loader. So in this session, we will profile our code, and for that you need to import these tools from torch.profiler. This is a standard model. I've talked about that. Let's see here what is changing. To profile the training, first you need to define the activities you want to measure. So we are going to follow the CPU and CUDA activities. I don't want to talk about these, but record shapes, I think that's obvious what this means. We are going to record the input-output shapes with that. We will provide the memory for sure with stack 2. I think I left this on 2 for debug purposes, but it doesn't matter too much right now. This line is very important here. If you want to profile your code, you would want to profile your running, the wait means how long should it wait until it starts profiling, then a warm-up. This warm-up is not going to be registered, but it is going to run. So it's profiling your run, but it's not going to save those profiles. It will discard it. Then we will have an active 2 cycles in which the profiling is being done. Then the repeat equals 1 means that we don't want to measure the whole training session. We just want to measure it once and leave it leave the model to train. Okay. And for the reason for that, like why do I need to do it like this? Because if I want to provide the whole training session, that would generate an insane amount of data that couldn't be read properly. I've tried it before. Unfortunately, I ran into this bug a couple of years ago. So just leave it as this. More precisely, you should during your live training sessions, you should wait for the first and the second epochs. So you shouldn't profile those epochs, because in that 2 cycles, in the first cycle, more precisely, in the first epoch, the training starts with copying the data on the GPU memory as well. So it's going to be much slower than the later epochs. So you don't want to do that. Of course, and the model layers are also distributed among the GPUs as well. So you don't want to wait for those. That's why if you, for example, put a weight equals 1 here, should be better. But let's just leave at 0 right now, and let's continue. Other than that, there is nothing really important with this code, and this is just a baseline for comparing the profiling between different kind of trainings. Okay, and let's see the bash code. We are going to load the AI module on the Leonardo supercomputer, and there's nothing else here except the torch run. For some cases, I couldn't receive an output from the Leonardo, but instead of torch run, you could use Python as well. I just used torch run because somehow I didn't receive the output properly. You should leave it as it is, but at home I recommend using Python. Okay. And let's run. I hope I'm using the proper reservation. All right, it's running. And I'm going to show you how to read the profiling. Okay. No. So the profiling file has already been created on the in the home folder, in the training folder, but we need to see it. And for that, I need to forward the port because we are going to use TensorBoard. My port will be this one. But you should use another port because it's not going to. I think you are going to see my results, or you will not see anything if I use this port. You should use another port if you are connect with the Leonardo. I am putting. I'm not putting it. I put it in the chat. And now I have forwarded the port. And as you see, there's the profiling file in the logs. So we want to see this profiling file, but we want to visualize it. And for that, I already forwarded the port. And I think this is what I should write in. No. I'm sorry. Did I do something bad? A momentary pause. That should work. I did something bad, I guess. Oh, yeah. Okay. My bad. I share my screen again. So to use the tensor board, you need to load profile, the deep learning, yes. And I see there's a problem. Let me see. Oh. Yeah. Anybody else experiencing the problem that has been put to Discord? Or is it running well? Oh, let me see. And this one. Not this one. Sorry. Oh, it's a copy tone. Not that. It's running for everybody else. I don't know what could be the problem. Oh, yeah. Yes. Okay. So, all right. Okay, we were at visualizing the tensor board, and for that you need this command. So first of all, you need to import the Gineca AI environment. Then again this one. Can't believe it. Yes. Then you need to specify the path where your logs are saved, and I'm going to just copy this code. Okay. There's another unexpected error here. Okay. Since I already tried this one out, it should work. So I'm just going to copy this command, change the port, and that's it. Should be good. Good. Not good. Oh. So I think you are using the my port number, but it doesn't matter. I'm just going to change it to something else. Don't follow me with the port number. Just let me do my stuff, and I'm going to show you what you can expect from the tracing. Okay, it should work. Yes, yes, yes. Okay. Good. I think everything is good. And if you've done everything properly during the profiling stuff, you should have, because the code was already ready. You should see this, and from this dashboard we need this option. So on the left side here, you see the trace option, and this will show you. Yeah, I see somebody else has a problem as well. So I am going to copy the command again, just to be extra sure about that. And I think that should do the trick if the training has been done properly. Okay. All right, let's move forward. So in the profiler, you will see a lot of processes on the CPU here. Like this is a forward method called here. And you see the GPU processes as well. if you see these small little specks here on the screen, don't be frightened. You can read them as well. For example, here it's this one is happening on the GPU, and if I want to say what it is, it's an activation of some sort. So you see it. We don't want to go too much into detail about the profiling. What you should see on this screen, that there is a lot of processing happening here on the CPU, and some of the processes are happening on the GPU. Yeah, I see the arrow. Yes, that data should have been already included. So you should see a data folder here. I think it's already included in the exercise material, but I will check it just to be sure it's not the data problem. Yes. Good. Yeah, the data is already there. Yeah, see, so if you don't have the data, you just need to set the download equals true. And that should do the trick if you have an internet connection, even on supercomputers that have internet connection on the compute nodes as well. That is no issue. It's pretty straightforward in PyTorch. Yeah, but I uploaded the material to Git without the data because Git doesn't allow us to upload so much data. Okay. All right. So at this point, you should reach this point before we move forward. If there's any error, please write on Discord and I will try to help. So it's a 5 minutes break until everyone is writing down the errors, if there's any. So for Theo, that is the right command. But if you are not on the supercomputer on the Leonardo, or you are, I'm showing you. So as batch run no-mp should be the command. And inside this, just let me put this down. Inside this file, you should pay attention to the account you are using. So if there's the account is bad, yeah, and you can check your account with saldo -b. So for me, there are two accounts, this one, and I submit the job with the CASTIEL account here. If you mistype anything or you don't have an account, a CASTIEL account, you need to change this batch script, and that's it. Oh, and of course, if you don't have your modules because you don't run on the Leonardo, and it's not going to work with the same environment as well. But you can load your own environment like conventionally if you have PyTorch already installed in for example Conda, then Conda activate PyTorch and etc. etc. Okay. The next. Yes, we would so is that you don't pay too much attention at this part. What you should really pay attention during if you are a beginner on this field, like you haven't done before any optimizations during your trainings, or you are new to deep learning, I recommend using this dashboard where it clearly says that GPU 0 has low utilization. After that, you see this part, you go to this, you see the trace, and you see that the GPU is not really performing very good. And you need to see the preceding events here. Like you see this line, I clicked on this one, and I want to know why it is starting so slow. And here are the processes that precedes that process. So these trace bands here on the screen is quite talkative if you see them, for example, on this part. The first layer takes a lot of time to initiate and etc. But if you want to know more about what is causing these errors, or not the errors, but the lags in your code, you want to know more about that. There are not too much documentation about this, like human readable documentation. I mean, what I usually do is I grab the trace file, give a large language model, and let the large language model to interpret that, and let the large language model to point me to the right direction where I should look at. Usually that does the trick because these large models, the cutting edge models, are quite capable of processing a large amount of data. So that's what I usually do. Other than that, I think it's the PyTorch official documentation where you can see more about the profiler, or what you can also try, since it is based the NVIDIA profiler, you should see the NVIDIA profiler documentation as well, how to read it. So that's my recommendation. Okay, I think we are quite done with this part, and we want to change the device ordinals and see what is happening on the GPUs if we distribute the models between the GPUs. Okay, and I am going to close this one, stop the tensor board, and let's go to the next example. And the next one is multi-GPU MP disorder. And this is how you distribute your model between the GPUs. As I've told you before, you only need to use device ordinals here to put the layers to proper devices. I see there's another error. Oh. Yes, for Conrad, connection refused. I got the same error before. Here, somewhere. Yeah, do you see this? This part. The connection refused is happening because you did not start the tensor board. So you need to start the tensor board, select the proper port number just for yourself. Don't tell anybody else, and it should be fine. The analysis when okay, I think you. Oh, that is the name in the Discord. So the question was, can I repeat the analysis when you provide the application? I will show you how to do it again. I will show you the context manager that is written for that. What you need for the context manager is this one. We are doing it again just to be sure that everybody gets it. So nothing, you didn't miss anything yet. First of all, for the profiler, you need to import the proper tools. This is the line you need for the profiler, for the Torch profiler. Torch profiler is, by the way, it's as you see, it's an embedded function in PyTorch. Then you need to write a context manager, and with the context manager, you need to define what kind of activities you want to follow. And these activities will be read by the profiler. Oh, yeah, sorry, forgot to with profile. Yes, didn't write anything else here. So the profiler will read in what kind of activities you want to follow. So again, we need to follow, we want to follow the CPU activities and the GPU activities as we described it here. We want to record the shapes. Again, it's left in here because I debugged something with it. I don't know exactly why it is needed here. It's an older code, sorry. And we profile the memory, of course. I will show you the memory profiling as well. And then you need to define the schedule for the profiler. So wait means you wait for X cycles until the profiler starts to record things. Then the warm up is when you record the things, but you don't save it. The active is when you log the activities on the on the devices, and the repeat is set to 0 if you are going to monitor the training continuously, and 1 if you want to repeat this logging for 1 cycle. Yes, and I failed to mention before, but the profiler needs to be moved. So with the profiler prof.step, we are incrementing the steps in the context manager. So if I just remove this line here, the context manager will not work at all. So we need to increment the steps in the context manager. Other than that, it's not going to work. Okay. Did I miss anything else? Yes, here we say that you should save the logs into this folder, and then we start the training as usual. So, okay, I hope that helps. Yeah, I'm bad at explaining things, so I really hope I'm doing a good job. And let's continue. So this is also going to be profiled, but now we are going to distribute the model layers between the workers, between the GPUs. And to do that, first you need to put the layers to the proper devices. For that, you only need, compared to the other code, I'm going to show you. See, there's not much difference between these two codes. The only difference here is the not parallelized code doesn't have device ordinals, and that's all the differences between them. And in here in the layer-wise model parallelization code, we put the layers to devices. For example, the flatten and the first two layers with the flatten is going to be put on CUDA 0, and then CUDA 1, and then CUDA 2, CUDA 3. And then we also need to tell PyTorch that we are going to forward the output of those layers to a different device. So right now from CPU, you should just imagine that it was like this. So I'm not writing it, but it was coming from CPU. And first you need to put it to a GPU. Without this, it's not going to work. Then if you remember, the layer 3 is on a different device. And for that, if you want to use a different device, you need to tell the PyTorch that put the output from layer 2 to the CUDA 1 device. So this FC2 layer is on the first device, but FC2 layer should forward the output to CUDA 1, to the second device. Yes, and so on. It's obvious after these pretty easy steps. And I told you before, you need to put the images to CUDA 0. And of course, we use the non-blocking true here. So the communication is not going to be blocked between the workers. If you want to know more about communications and, for example, MPI standards, more so in PyTorch, I refer to the official documentation here, but we shouldn't block the workers. That's why the communication is set to non-blocking communication. Honestly, I haven't tried if it's working without non-blocking, because this code has previously been ported from a DDP code, and I'm just curious if this is going to help you. Hope this helps. Yeah. So with DDP, as previously, I think Casper already told you thoroughly about DDP and told you how to properly use these techniques. Yeah, and as I see, if I don't use the non-blocking communication, and if I use it and don't use it, it doesn't matter for layer-wise model parallelism. So there's a small bug in the code. Nevertheless, it runs the same. So it doesn't matter if you use non-blocking or blocking communication. It shouldn't matter at all. And that was my thought as well when I saw this line. Okay. Yep. We put it down. So you need to, as I've mentioned before in the slides, you need to put the images to the proper devices. Since the first layers of the model are residing on CUDA 0, you need to put the inputs to CUDA 0 as well. And the labels to CUDA 3, because the outputs is generated on CUDA 3, and to create the loss with the outputs, you need to have both kind of data on the same device. Without that, it's not going to work. Like just for demonstration, I'm putting it in the wrong device just for fun. Okay. Is it? Something is off. System is not so responsive now. I don't know what is happening. I hope it's not my bad. Oh, it's right. Good. Slurm is having issues. Thank you. So again, I intentionally put the labels to the wrong device just for demonstration. What this will cause, and let's wait for starting job. Okay, any problems so far? Okay, it's running now. All right. And now you see the error message I produced with the wrong device ordinals. And it says somewhere here, yep, expected all tensors to be on the same device, but found at least 2 devices, CUDA 3 and CUDA 1. That is because we put the labels to the wrong device. This is why you should put the labels on that device where you expect the output. So I'm putting it back to the good device, to CUDA 3. Okay, that was an error. I think it's solved now. So from the training, we already have the log files here. I don't know what is going to happen if I have multiple trace files here, so I'm just going to remove one randomly. Oh no, not bad. I bet I removed the good one. Perfect. I know why we have. And of course, since the port is already forwarded and we didn't close the terminal, hopefully, we can see the trace files already. Yeah, so there's our trace file. And I want to see it. So before I see it, because I've learned from my previous mistake, I need to start the tensor board. Don't forget to start the tensor board because it's not going to work if you don't do it. Okay. Yes, the communication between the layers in the same device is handled automatically. So, like, if is the same as a conventional training if you use only one device. So if for example layer 3 and 4 is on the same device, then you don't need to tell PyTorch where to look for. It's going to move forward automatically with the training. You only need to tell PyTorch where to look for the device when the device is changing, except for distributing the layers. Like if you don't put your layers on the device, that is, I think that's going to cause issues. But during the forward pass, you just need to tell PyTorch when the device is changing. I'm going to show you that one again. So between layer 3 and 4, the device is not changing. That's why I didn't tell PyTorch where to forward the tensors, the outputs from layer 3. TensorBoard is already installed on the Leonardo supercomputer. It's in the environment we are loading in each training. But if you don't have TensorBoard, I think that's not too difficult to install. I think you can install it through pip, the pip package manager. Okay, let's see the trace file of the layer-wise model parallelism, and this is going to be a bit more interesting than before, since we have 4 GPUs here, and 4 GPUs, as I have shown you before, is going to forward, like if you see it here, this is the forward passing here, and each given time, like here at 200 milliseconds, there's only one device active or no device active. That is why I told you this method could be inefficient. If you have 4 devices, you are working on 4 devices, then that means the maximum efficiency you can expect from those devices, if you have optimized everything pretty well, it's a maximum of 25% of total efficiency. And so this is the forward pass here. The tensors are passing through the activations, passing through. Then this is the phase where the gradients and the loss is going to be calculated. This is gradient calculation here in the backward pass. And then, as I have told you before, after the gradient calculation, we see that the weights are updated synchronously. Not perfectly synchronously, if you look at here, because it shows a similar pattern, but it's kind of synchronous, and it's not that slow, not as slow as the forward and backward passing. Oh, I haven't seen this pattern so nicely before, so it's nice to see it. Good. So this is the bubble. We really don't want to see it, but if you have a large model, then this inefficiency will be seen here. And pipeline parallelism, for example, gives you a solution for this bubble. I'm going to mention how pipeline parallelism helps to solve this issue, but we are not going to do any pipeline parallelism in this session. Good. Okay. Okay, I see there's not too much error. You are handling it pretty well. So we can move forward, and I can show you how to do CPU offloading. Not this one. Honestly, CPU offloading is not so different than what I had shown you before. Like layer-wise model parallelism between the GPUs and the layer-wise model parallelism between CPU and GPU is quite the same, and you can merge not just merge, you can hybridize the devices as well. And in the next case, I just put the first two layer to the CPU, and that's all I did here. If you look at the bash. So I changed the device ordinal here and here and here because I needed to put the FC2 and 3 layers to different devices. Then in the forward passing, don't forget the forward passing. In the forward passing, you also, in the forward method more precisely, you also need to put, you need to tell PyTorch where to send the input in this case. So you need, but I wonder if I remove that CPU part here, will it still run? I think it should, but that's a homework. If you want to try it without this device ordinal here, you can try it as well. And this is all. This is the CPU offloading. If you previously I told you that if you have a large model, like the model is almost 40 gigabytes of memory, and just for safety concerns, you want to put some of the layers to the CPU. It's either the first or the last layers. I would say first is better. Then this is how you do it. And you should always think about only of the first layers and the last layers. Because if you put your middle layers or hidden layers on CPU, then there is going to be a double communication overhead compared when you put it on the beginning or at the end. Because like from CUDA 1, you need to forward the output of, for example, FC3 layer to CPU. Then from CPU, you also need to forward the output to FC5 layer. And that depends on the interconnect, how fast that is going to be, but you shouldn't use a middle layer. You should only change devices when it is really necessary and the least amount of time. This is what I'm trying to say to you. Okay, and in the code, nothing else changes. This is the same. You can run it. You can see the log files. You can see the profiling of this code. It's just a small example, nothing really extra. Okay, and I should already have the log file. And let's see what is happening. If I use CPU as well during the training. There's a question if there are enough GPUs is offloading to CPU improving the performances. I think not. So the GPU will always, let's say always, outperform CPUs. So the GPU is better, but you don't want to anger the system administrators by running your model in low efficiency, like you are using 2 GPUs and both GPUs can only run in 50% efficiency. If your model can almost fit to GPU and you can upload to CPU as well, and maybe, just maybe, I haven't tried it, but maybe you can also parallelize that task with distributed data parallel as well. I think that could outperform the GPU pair setup. I think it should work if you upload some of the layers to CPU and you run it in 4 copies in a 4 GPU setup. But and I don't see why it shouldn't work, but you need to try that out. Okay. Yes, we are wasting GPU cycles. Exactly. Yes, exactly. Like Ram9 says in Discord that here we are wasting GPU cycles instead if we send batches in sequence to device without keeping it idle, can better utilize the GPU cycles during training. Yeah, this is pipeline parallelism that can have this problem. So pipeline I'm going to talk about pipeline parallelism shortly, because that is exactly what it achieves. Okay. Oh, sorry, I wanted to show you the TensorBoard. Okay, now it's working. So nothing really happens. It specifically says to us, I'm going to increase the size here, that GPU 0, 1, and 2, and 3, we're underutilized. Increasing batch size may affect the shape, blah, 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 blah. But we are underutilizing it. Oh, and I wanted to show you another thing, because we profiled the memory usage as well. We can see the memory usage for each device. For example, here's the CPU, here's the GPU 3, GPU 0, and we are way underutilizing each of these devices. And you can browse this part for yourself, and you can see which part of the training consumes the most amount of memory, I think. They are not clickable. They are not links. Okay, let's go to the tracing. What we will see if we upload some of the layers to the CPU. Nothing much. So here are the forward passing, because since we used 4 GPUs as well here, we should see that bubble as we have seen before. But if you look at the profile, these bands in the profiler, you can find your layers. For example, here is the layer 1. Let's see the layer 1. Where did I put that one? So the layer 1 is at the CPU. So it should be on the CPU, I guess. No. It should be. But to be extra sure, this flattened layer is on CPU. It's nowhere near GPU. And what we shouldn't see at layer 0 is something like CUDA operations. So this is pretty clear proof that layer 0 runs on CPU. That is proof 1. Layer 1 is running on GPU, I guess. And then we should have a flattened layer somewhere here. I think I know where it is. Yeah, there is our flattened layer, which is also not running on the CPU, on the GPU, sorry. This one is CPU, this one is CPU. There's nothing GPU related happening with these layers. But it is happening with these layers. Each of them are calling CUDA kernels. Good. And of course, the other clear proof that we are using CPU, that it is listed here as well. Okay. We don't have too much practices, but I still want to show you. So we went on with CPU offloading, we went on with the multi-GPU model parallelism techniques, and we have seen how it is looking if we don't use model parallelization as well. Since we are short on time, I'm just going to show you what is happening if we are running a model that is downloaded from Hugging Face, for example. So there is our efficient B0 model in PTH, extension, or in PTH format. Oh, not this one. I need. Yep. I'm just checking the code swiftly. Oh. I want to see how efficient that V0 looks like, so I'm just going to put it in here. I think that should be okay. It's running. Great. No module name, torch info. Oh. Yeah. Because in older versions, I think it's not going to work. Torch summary, was it? Let's try this one. Okay. In the meantime, I'm searching if torch summary is the right one. So torch info in the code I provided for you, torch info is not going to work because torch info is a later package, and instead of that, I think you should use torch summary. Summary. I think this is the one. Yes. Yeah. We see the model here. So I printed out the model. But this is how an efficient net B0 looks like. And model features. I don't want model features right now. Okay. So this is the whole model here. These are the layers. And there are more than 5 million parameters in total in the efficient net B0. And we divide this model to two parts. The first part is going to be 308,000 parameter large part. And the second one is 3.7 million parameters large. I did not try to divide this model equally at all. I did not do any optimization. I just put it in like, why shouldn't I? I didn't calculate anything for this model, which is bad practice. Don't do it ever. So the first 5 layer, okay, let's start at the beginning. So first of all, you need to load your model as a module. You loaded your model with this line. I think in older or newer versions, you need to use you need to set the weights only equals to was. I think it's true for older versions. Newer versions not necessarily need this part. Then I put another layer before the model because I needed to make the efficient net B0 model compatible with MNIST, and to do that, I needed to create a new conf2d layer before the efficient net B0. So this is the only addition to that. And I added to the model. Then the layer 1, which confusingly I call it layer 1, but it should be called like module 1 or part 1 or shard 1. The model features are distributed to by the layer. So the layer 1 is going to contain 5 layers from the original model and this layer as well. So 4 layers from the original model plus the additional convolutional layer. This is put to CUDA device 0. I did some tweaks and I decided not to use always CUDA 0, 1, etc. Because if you receive a different device ordinal than usual, then your code will not run. That's why I read the devices I received from the Slurm scheduler and converted them to device ordinals. This is a pretty small trick here. It's not too big of a deal. And then I created I think this is another addition here. So there's a classification layer here that is also put to device 1. Then the forward passing is happening as before, but now we only using, as you have seen here, 2 devices, CUDA 0 and CUDA 1, or CUDA device 1, CUDA device 2, CUDA device 0, CUDA device 1. Sorry. And that's it. That's all the changes. So now you see, if you download the model and you want to run it with layer-wise model parallelism, this is how you can do it. And other than that, nothing else really changed here. The scheduler and the profiler remain the same. The only addition here is that we are using the different device ordinals. I think we shouldn't go into detail and see the log files or the tracing, because what it's going to show us is that we have two GPUs working, and it's kind of going to look like the same. Okay, and here comes a bit more exciting part. I hope you can follow me, because now I think it's going to be a bit more confusing, but I hope that Caspar made a really good job and told you how to run a DDP job, because that DDP is appended with layer-wise model parallelism here. And it looks the same as Caspar told you before. So you need to initiate the communication. You need to get the local ranks. And what is tricky here, if you want to combine model parallelism with layer-wise model parallelism, that the device ordinals should be also, how should I say it? So in case of a one node, you will, and if you use it exclusively, like you are going to use all the 4 devices, you will know that you will have CUDA 0 to 3. In this case, if you are running your code in a multi-device, multi-worker, potentially multi-node environment, you need to be tricky about the devices here. And for the local rank, which is 0 for worker group 1, the device 0 will be 0, and device 1 for local rank 0 will be 1. And the same is true for local rank 1, where the first device is going to be device 2, CUDA 2, and the second device is going to be CUDA 3. It's a very small trick, but if you don't pay attention to this small detail, you will pull your hair out to find the issue. This is not handled automatically in PyTorch. You need to write the proper device ordinals. If you run your code in distributed data parallel, appended with model parallelism. Okay. And just to be extra sure that this runs as well, keep note that I didn't want to talk about distributed data parallel as well, because Caspar already told you that part before. I just appended or built on that material. And I see Slurm has issues again. Okay. Any questions so far?
Gyula,
Yes?
sorry, if we can have a 15 minutes break, if it's possible for you.
Yeah, I think I have half an hour long material left, but we can have a small break.
Yeah, just to stretch the legs.
Okay, 50 minutes. We will
Perfect.
see 4 p.m.
Perfect.
Okay.
See you soon. Thank
See you
you.
soon.
Bye-bye.
Bye. has a good implementation for that. So Lightning PyTorch is a wrapper around PyTorch, and in that layer-wise model parallelism can be easily implemented compared to PyTorch. So these are my recommendations. PyTorch in this context almost maxed out in this session, and I think the others during the later sessions will tell you how to use these wrappers. Okay. Oh, Mark, maybe you are not on the Leonardo. I think I've given every right for you to see it, but I don't know your user ID, so I cannot really help you there. So sorry, but there's the GitHub repository, and you can copy that as well. Just need to port it for your system. Okay, but let's go back to the material and continue with the last part. During the break, I started the EfficientNet B0 training. I remember that EfficientNet B0 model was divided among 2 GPUs. Was it the DDP? Yeah, sorry. DDP model parallel. Oh. Oh, I just confused myself. I started the DDP, but I wanted to show you how the previous training went. And as I told you before, there's nothing much extra about training on EfficientNet V0. You will see the same pattern, the same bubble here, the same inefficiency, but with a larger model. It's just for show. Okay, but the EfficientNet B0 has finished in DDP, and I just want to check out how much faster was the DDP setting compared to the no DDP set. Oh, I'm in the wrong folder here. So compared to the non-DDP setting, the DDP finished the job quite faster. So the DDP set in DDP, it has been finished in almost 2 minutes. And without DDP, it finished in 7 minutes. Why is that? It's a radical increase in performance. Almost quarter of the original time, but we used 2 nodes and 4 GPUs on each node. There's another difference here, and I think maybe you noticed as well, that I didn't use profiler here. So I left a profiler out of the picture because the profiler would create a separate log file for each worker group. So in this setup, we were working with 4 worker groups in 8 GPUs. And each one of those workers would create a separate log file for TensorBoard. That's why I didn't bother to create a TensorBoard from out of these traces, because it would be pointless. We would need to check each one of them out separately. Okay. Demonstration here is that you can combine a layer-wise model parallelism with DDP as well. Okay, and the last one is a large language model. So how you split a large language model, it's just the same as before. I created a pretty easy code here. You can use it really however you want. Let's first see how this Roberto model looks like. So this code shows you how to convert the model to a compatible model format. We save this model in this name. This is just for saving the model. This one. This one, yes. And I split the model to 3 parts. And I did a dummy inference on that model. So nothing really happened here. I used the same tricks as before. Put the model or the layers to different devices using device ordinals. And just run the model as before. I'm just running the model right now. And it's not starting yet. So the practice part basically ends here, and our session is almost at the end. And I almost already answered for all the questions before, and those questions also covered the parts I wanted to talk about. If you don't mind, I know I don't want to wait for this job to finish running, and I'm going to conclude our session shortly. Let's go back to the slides. In a moment. Okay, we left it here. Then we've done the tracing. I left some notes here, so you can see how to create a TensorBoard for yourself if you have TensorBoard installed. There are the commands you need to use. I already demonstrated this part. This is the layer-wise model parallelism with DDP. This is what is happening in the background. I've tried to put all the processes and passings here. So you see the forward pass here, what we've seen for one node, and the backward pass as well. The only difference between them is that we need to make them communicate with each other. And since DDP is already discussed in much depth before, I don't want to talk too much about this, but what was happening during the EfficientNet B0 DDP training is basically put onto this slide. So it shouldn't require any more explanation than that, as I see. Yes. So cases when you want to use PyTorch and model parallelism, some form of model parallelism is the distributed data parallel as well. But at that case, you have a large amount of data, and the small model you want to distribute among the GPUs. So each GPU will hold a copy of the model. We have seen a different setup for that as well. We've had a larger model. We pretended that we have a larger model, and we distributed the model layers between the GPUs. So we combined two techniques, the layer-wise model parallelism with distributed data parallelism. So if you need more memory for a model, then layer-wise model parallelism, tensor parallelism, and pipeline parallelism is the three method in PyTorch. I need to articulate in PyTorch that you need to think about. Other frameworks, wrappers will have different techniques, and the others during the later sessions will show you how to properly implement those techniques. And there are cases when you have both lot amount of data and a large model. As I've said before, we combined DDP with layer-wise model parallelism, but I think you can combine DDP with pipeline parallelism as well. I don't see the reason why not, and tensor parallelism as well. And of course, any other combination of methods you know of. Usually they don't exclude each other. At least as of this moment, I don't have anything in mind that could exclude each other. And yeah, that was the question. So let's talk about pipeline parallelism a bit and why I didn't show you that before and why it is more performant. So there was a question in Discord that pointed out that this method I was showing you is inefficient. Yes, it is inefficient, and one way to solve this inefficiency is pipeline parallelism. So this bubble during the forward passing and backward passing can be shortened or squeezed if you use a pipeline parallel strategy. And this pipeline parallel strategy is discussed in depth in the GPipe paper, or here on this side you will see the that Google also published their own research on the topic. I don't want to talk about that much. Pipeline parallelism is not so easy to implement in PyTorch. That's why I didn't do it, but it is more efficient than layer-wise model parallelism. And the other method you should be aware of is tensor parallelism. Tensor parallelism is also a technique that is harder to implement in PyTorch, but I didn't want to show you that. I wanted to originally, but during porting the codes to the Leonardo and from our system, I encountered an error of which I couldn't solve. So I'm sorry that I couldn't show you how to implement it properly, and I will not show you a code which has bugs. So forgive me that I under-prepared a bit this session, but I don't want to give you any wrong codes. Tensor parallelism basically means that if you have a very, very, very large layer, which cannot be fitted into one GPU with layer-wise model parallelism, you are not trying to, in this case, you're not trying to divide the layer, the model between the layers, but this is an interlayer division of the model. So you divide that layer among the workers. Tensor parallelism, I think, is also going to be shown you in later sessions. So I'm not going to go too much into detail about tensor parallelism. It is just for the sake of completeness to let you know that there are techniques to solve other issues that layer-wise model parallelism cannot solve. Okay, and I think that was all I wanted to talk about in this afternoon session. The point was in this session to give you usable examples and codes if you are new to model parallelization techniques and training or using large models. Then you can easily implement these techniques, and it's kind of, I hope it's easing you into more advanced techniques during the later sessions. Thank you very much. Oh, if there are any questions, I try to answer those. If there are none, then I think that is all. I'm going to look at the Discord channel, so if I see the questions later, I will. Yes,